In this video, we'll now discuss how to train a recursive neural network. So we've discussed the two main components behind recursive neural networks, the part that merges pairs of vector representations to obtain a new representation that covers more words in the sentence, and also the part which assigns a score for the quality of merges and from which we can get a procedure for determining what is the best tree structure according to the model. So the best tree structure in terms of the score it assigns for the full tree, and in order to get and infer the correct syntactic tree for a given sentence. So now we'll see at how we can actually train the recursive neural network to actually produce the true wanted parse tree for a given sentence that is provided in some training data. So I'll refer to y as the true parse tree for a given sentence, and y hat as the parse tree that's predicted by the recursive neural network using the procedure we saw in the previous video. So what we would like is for the score of the full tree y, which is the correct tree, so we call that S of y, to actually be higher than the score of the tree that we predicted, y hat, where unless of course y hat is actually y, in which case our neural network is doing the right prediction. But if it's doing an incorrect prediction, then what we want is for the score of sy to be higher than the score of the score of y to be higher than the score of y hat, so that next time around it's more likely that y will be the predicted parse tree. So an algorithm for trying to achieve this is that whenever y hat is not y, we just increase the score of y and then we decrease the score of y hat. So procedure for doing this would be to first take the sentence and infer the predicted parse tree, and then we will increase the score sy of the correct tree y and decrease the score of y hat, noted sy hat, by doing an update in the direction of the gradient of the score sy, the gradient with respect to the parameters of the model of the score sy, minus the gradient of the parameter with respect to the parameters of the score for the predicted tree y hat. So in other words, we have to take these two gradients and subtract them, because this is giving us a direction that will increase the score for y, and this is going to give us a direction that is going to decrease the score of the parse tree y hat. And now to get the gradients, each of these two gradients, and to then combine them to get a single gradient, so a single direction in which to update our parameters, then what we'll have to do is do regular backpropagation through the recursive network that follows the structure of y and y hat. So essentially for, say, y hat was a parse tree corresponding to that structure, then in this case it means we'd have a neural net which is taking the word representation here and here and computing a representation which is like a hidden layer at this level, and computing a hidden layer at this level by combining this vector representation with the vector representation here. From both of them we'd get as the output a score, the score of that merge and that merge, and these would be summed together to get the score of the full parse tree y. So that would be forward propagation, and then backward propagation would be to assume that we have a gradient with respect to sy of 1, and then moving in the other direction, back propagating the gradient with respect to all of our parameters to get the gradient with respect to all of parameters for that, for sy. And then if we wanted to get the gradient minus sy hat, then so imagine that y hat corresponded to a different parse tree, so maybe this parse tree here, then we'd be computing this vector representation and then this one, and from both of them we'd get a score which would be summed together, and this would give us sy hat. Then again we'd assume that the gradient with respect to sy hat is -1, because we're interested in the gradient in the negative gradient, and then we'd back propagate through the neural network that was constructed recursively using this syntactic structure of y hat, and then back propagate through to all the parameters. And so these two procedures would give us this part and this part of our update direction, and then we'd combine them by subtracting them, and that gives us the update direction to follow to update all of the parameters. So that's how training would proceed in this case. Now, in a parse tree, often the nodes are also labeled. They're labeled with respect to whether they correspond to a noun phrase or verb phrase, and using these labels are actually available in the training data. So one thing we could do is to just also add from each representation at every level, add connections to a softmax layer, which would try to predict what that label is. So instead of having just as from each vector representation have a score that is outputted, we'd also have other parameters of the neural network that would also try to predict what's the distribution over the label of that at that node. And then we could use the negative log likelihood of the true label as a gradient, which could be then back propagated through the whole network. And this we can only do for the true parse tree. Why? Because for the predicted parse tree, we don't necessarily have nodes that correspond to the original parse tree, so we don't know what the label should actually be. So this other backpropagation that we can do to integrate also the notion of labels at the internal node in the parse tree, we can only do it for the true parse tree. And so then we check what's the negative log likelihood at every internal node, and this would give us a gradient for those output layers, which would be backpropagated through the whole network. Similarly, as we backpropagate the gradient with respect to the score of the trees. Some other details about how training proceeds. In their paper, they actually use the word representation using the language modeling task of Colabert and Weston. And then, so they use that to initialize the word representations, and then they would fine-tune them essentially, because they use them as initializations. They would still train them using the recursive network training procedure that I've described. So this shouldn't be autoencoder. This should be network. So that's another detail that was important for getting good results. The other thing, which I don't want to describe in more details because it goes a bit beyond what we've seen so far, is that the training criteria they actually use for training the recursive network to give the correct parse tree is actually a margin-based criteria. Essentially, they don't want the correct parse tree to have a strictly greater, only a strictly greater score than any other parse tree y star. They actually want the score, the correct parse tree, to be at least some margin greater than the correct, than any other parse tree, and that margin for a parse tree y star is going to be this delta y star here, which corresponds to essentially the number of errors in predicting y star when the true tree is y. And this number of errors is actually the number of incorrect spans. So just give an example to make this more concrete. So imagine that the true parse tree was y, and then we're considering what's the number of incorrect span with respect to, say, predicting y star here. Then there would be one incorrect span, and that's because at this internal node, we're spanning the words from position 3 to 4, whereas in the predicted, or this other incorrect parse tree y star, there are no nodes that span from 3 to 4. There's instead a node that spans from 1 to 3, which is not present in the original, in the true parse tree. So we don't incur an error for merging this here, and that's because we also merged these two together, and also we don't incur an error at the global tree. So at this node here, because this is spanning all words, and similarly here at this level of the parse tree, we're also spanning all words. And it turns out that using, we can just do a very small modification of the approximate inference algorithm that we saw before, which is essentially a beam search kind of approach. So we can actually modify it to instead try to find the tree that most violates this margin criteria. I'm going very fast over this. I don't really want to give more details about that, but I encourage you to know more about this training procedure. If you still have questions, to look at the Socher et al. Paper where more details is given about that. And with respect to this training procedure, essentially corresponds to trying to do approximate structured SVM kind of training of the score given by the recursive neural network. But again, to get more details about everything that's described in this video about the training procedure, I encourage you to look at this paper here. And in terms of the performance, if we look at the performance for syntactic parsing, which is usually measured using the F1 measure, the recursive neural network gets a performance of 90.25%, while one of the state-of-the-art parser, the Berkeley parser, gets 91.63%. So it's a little bit worse, but it's quite close. And so that's pretty satisfying. If you look at the paper by Richard Socher, you actually see that you can use the same algorithm for also parsing visual scenes. And for visual scene parsing, you actually got at that time state-of-the-art results. So while it might look like this is only applicable to parsing sentences, you can also parse visual scenes, and in this case, it actually gets state-of-the-art results. And finally, in the paper, they also provide an analysis to try to see these representation of phrases and in sentences, whether they actually capture similarity that's meaningful. So for instance, if we took that sentence, Fujisawa gained 50 to UNC. That's because this is for a non-node word or an OOV word. That's just the token they use for representing OOV. And we look at other sentences that have or phrases that have very similar vector representations. We get phrases that indeed maintain some of the, have very similar information as is contained in this particular phrase. Again, in another example here where the dollar dropped was judged to be similar to the dollar retreated or dollar gained or bond prices rallied, where here we get a fairly different phrase than this, but we see that it's talking about similar concepts. So again, I encourage you to look at this paper by Socher, and there are actually many more extensions that have been developed in the following years, and so I encourage you to also look at that. And that's it for recursive neural networks.